Hi everyone, it is Lauren and I am the intern at D Squared Consulting. So today on D Squared Classroom, we're going to start a little mini series on material properties. Now everyone kind of has a gist about material properties. Like we know what materials are stronger than others. You know that if you make a house's foundation out of a metal, it's going to be a little bit stronger than if you make it out of wood. Or if you're standing on a chair to get something on the top shelf of your cabinets, you know that you might want to choose like a metal or wood chair over like a thin plastic chair. Now, how do we get the numbers that back up these gists on material properties? And us as engineers, we always like our graphs. So today, we're going to talk about a stress-strain diagram and how we can get useful numbers and quantities that help us determine material properties. So let's dive in.
So when you try to find out the material properties of a certain type of material, what you do is you put it into this tensile testing machine. And essentially what that does is it holds on to both ends of the material and pulls it. And as it pulls it, it generates useful data. This useful data is generated on a graph with stress on the y-axis. Stress is force divided by area. And essentially, this is just a unit of the internal forces that this material is experiencing. So essentially, stress is how hard are you pulling it? How much force is this material experiencing? On the x-axis of this graph is strain, and strain is the change in length over the initial length. So essentially this is a measurement of how much your material is deforming. So everyone knows that when you pull a rubber band, it expands and it gets longer. So strain would be how much this rubber band is changing in length. So when the material is being pulled, it will start out at the origin, and as you pull it farther and it deforms, the graph goes up. And essentially, the first part of the graph is relatively linear. And there's a useful bit of information that you can get from this linear portion, and that is the Young's modulus. The Young's modulus is defined as the slope of the line of this linear portion of the graph. At the end of the linear portion, we have a point called the yield strength. And we're going to come back to this and describe what it actually means. After the yield strength, we keep pulling on our material. So we keep applying stress to our material and our graph continues to go up. However, this time it's a curved region instead of a linear region. Eventually, we reach the max stress, which is the ultimate tensile strength. And essentially, this is the stress in which it endures, and then it starts to fracture. So it's the mass stress it experiences until the actual fibers of the material starts to break. And this breakage helps relieve some of the stress the material's experiencing, and our graph starts to slope downward. And our graph continues to slope downward until we reach the fracture point. And this is when the material actually breaks completely in half. So at this point in our tensile testing machine, our two ends of the material are completely split apart and are not even connected. The material has completely broken. So now looking at our graph, and I've kind of hinted at it throughout this episode of D Squared Classroom, but there are two specific portions of the graph. We have the linear region and the curved region. And these are separated by that yield strength. What I talked about before that I said we'd come back to, well, here it is. The yield strength is where your graph turns from a linear region into a curved region. And this linear region corresponds to elastic deformation. And what that means is when you pull it, it snaps right back into place. So think of a rubber band. When you pull a rubber band and you let go, it snaps right back to its original shape without any change. That's elastic. It changes and it goes right back to normal. Once we get into that curved region, we get plastic deformation. And what this means is once you stretch it, even though it might change a little bit when you release it, it doesn't go back to its initial shape. So think of like silly putty. If you ever pulled that and let go, it doesn't snap back like a rubber band. It stays stretched like that. And that is plastic deformation. And with that, we've covered a lot of the useful information you get when you put a material in a tensile testing machine and you generate a stress-strain diagram. Stay tuned for next episode when we compare different types of material and the different graphs they generate.